Hello everybody. In this video we will discuss how to prepare ether. So let's start with how we can prepare a symmetric ether. So symmetric means on either side you have the similar carbon chains. Okay, so CH2, CH3 on the right side. On the left side you also have CH2, CH2, CH3. Okay, so these reactions you can actually make from simple alcohol. So this is how the industrial scale reactions happen. So you have your alcohol and then you do this reaction in acid catalyzed mediums. Okay, so let's not worry about equilibrium and everything. Let's focus on how we can draw those mechanisms. Okay, so you have your ethanol. So what's ethanol has? Oxygen, and oxygen has lone pair. And when you do this reaction in acid catalyzed medium, so let's say you are this. So the proton, so the lone pair here will abstract a proton from water or hydronium ions. So because this is acid catalyzed reactions, so then what would you make is CH3, CH2, OH, and H. So this hydrogens right here has come from here. Okay, so now oxygen has 3 bonds, so it has given electron away, so it should have positive charge. So every time you have a positive charge on oxygen, every time you have 3 bonds around oxygen, just remember 3 bonds positive, 2 bonds neutral, 1 bond negative. So oxygen has 3 bonds, so it's going to have positive. Okay, so now what's the next goal? So you create a positive charge, so your next goal should be how can I neutralize it? So the way the reaction will move forward is if I bring these 2 electron here, there are 2 electron there, if I bring back to oxygens, so the water is going to go out of your molecule. But if the water goes out, so let's say the water goes out. Okay, if the water goes out, so you notice what's happening here. You are creating a carbocations, right? But we know that primary carbocation is not very stable. So it's not gonna go away on its own. Instead, 2 things will happen. Let me bring this back. So simultaneously, another alcohol molecule will attack. So this is gonna be SN2 attack. So at no point this carbon atom will be sitting empty bond with an empty bond, empty location. So both the attack of the group and the removal of the group happens together. Okay, so if that happened, so this is an SN2 attack. So this ether synthesis is good for primary and possibly secondary alcohol. Not gonna be good, but it's doable. But again, it has to be symmetric. Okay, so now we got a situations where, okay, let me color code. So we got CH3, CH2, and then the oxygen from the red came in attack. All right. So you notice again, oxygen has 3 bonds at the center. So what should we do? It should have a positive charge. And then the last thing we will do is neutralize the positive charge on oxygens by removing this hydrogens. And who would remove it? Well, we got plenty of proton abstractors. So this would be able to, another alcohol can come in and take it out. So if it took out that extra proton, then we have our symmetrical ether. And then the byproduct would be CH3, CH2, OH2 plus. And you see this CH3, CH2, OH2 plus is the same thing as this one, right? So these things can recycle over and over and over again, right? So these things can recycle. Let me highlight this. So this thing is exactly the same thing as this here. So this, both of this can recycle over and over and over. Okay. So that's how you prepare this symmetric. So this method, this is the industrial process. So this is good for symmetric ether when on both sides of the oxygen you have the similar type of group or the same group, and good for, so this method is good for symmetric ether, and this method is going to be good for primary alcohol as a starting material. With secondary, the yield could be very low. Tertiary, it won't happen. Okay, so that's pretty much. So let's look at the another type of ether synthesis, Williamson's ether synthesis process. So this is also a industrial process. So what if your goal is to prepare this? Okay, I'm gonna draw the whole thing, that way you can see what exactly is happening. So what if you want to prepare this ether? Okay, so so this is tertiary butyl methyl ether, or people call it MTBE. So how would you prepare this one? Because on either side you got different groups, right? So the way we're gonna do this, so let me try to write the correct way, then I'll explain the wrong way. So let's say you have tertiary butyl alcohol right there. Okay, so we know that the hydrogen on alcohol is acidic. So this hydrogen is acidic hydrogens, right? So this is, so the acidic hydrogen. So this hydrogen can be deprotonated using a very strong base. So we're going to use a strong base called sodium hydride. So hydride is basically H minus, right? So this is our sodium hydride. Okay, so the hydride ion is a very, very strong base. So this is very, very strong base. Okay, so what the hydride ion will do is it will abstract, the proton, right? So so let's draw the product from here. So we got CS3, CS3, and we got O minus. Okay, and obviously you'll make hydrogen gas that will go out of your reactions. So you make O minus. So now this O minus would work on a alkyl halide, which is the same portions, this one here. So if you notice here on this side, there is a methyl group, right? So you want to have the same methyl group, but it is attached to an halogen with a good leaving group. So we will use iodine. It works really well with the iodine. So now this can have an SN2 attack. Okay, so the SN2 attack. So, and boom, we got our product. CS3, CO, CS3. Okay, so we got our SN2 attack. So one thing you want to make sure is this alkyl halide here. So this alkyl halide must be a primary halide. Okay, hopefully my spellings are correct. So this must be a primary halide. Worse, like you can do secondary, primary, and maybe I should put there. Secondary is doable, but it's not going to be as productive. So it has to be primary or secondary halide. So let's say if I try to flip it, okay? So what if I flip it on the other directions? So let's say I will start with CS3OH. So instead of starting, instead of starting with this butyl alcohol, if I try to flip it, okay, so now I use the same sodium hydride. I will make CS3O minus because the acidic proton will be gone. So this proton will be gone. So this hydrogen goes out. Now I will use this as a nucleophile. So I will use this as my nucleophile. Okay, this looks bad. So I will use this as a nucleophile, and I will use to act on this. So if you try to do this, where you attack on this carbon atom and remove this, remember SN2 attack is not possible on this tertiary carbon atom because it is way too crowded. So this reactions is difficult to achieve because the carbon atom, when I say the carbon atom, I meant, okay, not that color. I meant this particular carbon atom is too crowded. All right. That's why it's not going to happen. Okay. So if you want to design a synthesis, try to put your halide on a carbon atom on a primary halide. So maybe let's see, let's do a quick problem. I think we are going slightly over, but that's okay. And I will give you a shortcut. So let's say, how would you prepare? I'm putting random molecules here. Let's say, yeah, let's do this. And maybe this. Okay, so you have something like this. So how would you, what is the best method to prepare this one? You can do anything. So how would you solve this problem? So let's try to identify what's on the left side and what's on the right side. So on the left side, we got this. And on the right side, we got this. Okay. Maybe I will draw slightly better. This is on the right side. So let's try to separate. Okay. I am going to write here CS3. The left side is CS3, CS2, CS2, OH plus CS3, CH. You can use the combination of these two, or there is another way. I could put my alcohol. So you see the alcohol here and the iodine here. So I could flip it. The other method I could use is I could use this CS3, CS2, CS2I plus CS3, CH, CS3. Like if you see ever in my videos mistake on hydrogens, like probably it's a silly mistakes. Okay, so that's pretty much we have here. So which one is the best method? Okay, so if you notice in our mechanism, there is always an SN2 attack happens on our alkyl halide. Now this alkyl halide must be a primary or at worst secondary alkyl halide. Okay, so let's look at here. So you gotta look at your halide, the iodide. So what kind of halide is this one? Iodide. Look at the carbon atoms. the one that is connected here, this one, and maybe here, this one. Look at this one here versus this one here. So this one is a secondary halide. Why secondary? Because this one is connected to 2 carbon chains. However, on this particular example on the right side, this one is a primary halide. By the way, you can use bromine chlorine as well. So that's your primary halide. So we know that primary halide works the best. So this one works better. So this method would be a better method to do this one. So let's try to do this method. Okay, so I will start here. So you start with your alcohol first. CH3CHOH. And then you treat with sodium hydride. That will deprotonate. That will take out your acidic proton. CH3CHO minus. Okay, so this will take out your proton. Okay, I'm gonna draw this out. Okay, and then you treat with your halide, which is CS3, CS2, CS2I. So this would have an SN2 attack. And bingo, we made our product, CS3. I'm trying to color code. Okay, so we made our product, CS3, CH, CS3, O, and on this side, we got the green molecule, CS2, CS2, CS3. So if I had used this method, the second step, the step 2, would have been on a secondary halide, which would have been a not good idea. Okay, so that's how you solve the puzzle. So if you're given these questions, you look at the molecule, split into 2 possibilities, like split it here on either side, see what's connected on either side, and attach OH on one side, iodine on the other side, and then flip it, attach iodine on one side and OH on the other side, and see which one of these example has primary halide. Like try to compare their halide, and whichever has the lower number, that's gonna be a better method. All right, let's stop here. I think I went a little bit longer on this video.